So you have experience with magnetic confinement. You have experience with inertial confinement. Most of your work has been in magnetic confinement.
Yes,
But let's sort of talk about the sexy recent thing for a bit of a time. There's been a breakthrough in the news uh, that laser-based inertial confinement was used by DOE's National Ignition Facility at the Lawrence Livermore National Laboratory. Can you explain this breakthrough that happened in December?
yeah. So it goes to the set of criteria that I talked about before about getting high energy gain. So in the end, what are we after in fusion is that we basically assemble this plasma fuel in some way, and we provide it a starting amount of energy. Think of lighting the fire. And what you want to do is get back like significant excess gain from the fact that the fusion is making more, is releasing the energy. So it's like the equivalent of like we want to have a match, a small match, light a fire, and then the fire keeps us hot. It's like this is very much like that. So as I said, we've made many of the, and what do I mean by we? It's like the fusion community has pursued aspects of this through a variety of different confinement methodologies. Is that the key part about what happens? So what was the threshold we had never gotten over before was that if you only consider the plasma fuel, not the total engineering system, but just the plasma fuel itself, we had not gotten to the point yet where basically the size of the match was smaller than the amount of energy that we got from the fusion.
Is there a good term for when the output is greater than the input?
Yes, there is. Well, there's several special definitions of this. So one of them is that if you like in a fire, if you light a match and you have it there and it's an infinitesimal amount of energy compared to what you're getting out of the fire, we call this ignition, which makes sense, right? This is like what our own sun is as well too. So that was not ignition in that sense as well too. So what we call this is scientific, the one that I just talked about, which is for some instance, when I get enough fusion energy released compared to the size of the match, we call this scientific break-even. Break-even. And it's because you've gotten past the fact that this is unity now at this point.
What is fusion gain, or as using the notation Q from the paper overview of the Spark tokamak, before we talk, using just the same kind of term?
Yeah, actually, so the technical term is Q, capital Q.
Oh, so people actually use Q.
We actually use capital Q, or sometimes it's called
Q is taken.
Q sub P or something like this. Okay, so this is... Which means what it means is that it's in the plasma. So all we're considering is the energy balance or gain that comes from the plasma itself. We're not considering the technologies which are around it, which are providing the containment and so forth. So why the excitement and so? Well, because for one reason, it's a rather simple threshold to get over to understand that you're getting more energy out from the fusion, even a theoretical sense, than you were from the starting match.
Do you mean conceptually simple?
It's conceptually simple that you get past one, that everyone like when you're less than one, that's much less interesting than getting past one, because
so there's a really big
you start to get energy gain,
to get past.
But it really is a scientific threshold, because what QP actually denotes is the relative amount of self-heating that's happening in the plasma. So what I mean by this is that in the end, in these systems, what you want is something where the relative amount of heating, which is keeping the fuel hot, is dominated from the fusion reactions themselves. And so it becomes, it's sort of like thinking like a bonfire is a lot more interesting physically than just holding a blowtorch to a wet log, right? There's a lot more dynamics. It's a lot more self-evolved and so forth. And what we're excited as scientists is that it's clear that in that experiment that they actually got to a point where the fusion reactions themselves were actually altering the state of the plasma. It's like, wow. I mean, we'd seen it in glimpses before in magnetic confinement at relatively small levels, but apparently it seems like in this experiment, it's likely to be dominated by self-heating. So that
makes it a self-sustaining type of reaction.
It's more self-sustaining. It's more self-referential system in a sense, and it sort of self-evolves in a way. Again, it's not that it's going to evolve to a dangerous state. It's just that we want to see what happens when the fusion is the dominant heating source.
And we'll talk about that. But
Yeah.
so there's also another element, which is the inertial confinement. Laser-based inertial confinement is kind of a little bit of an underdog. So a lot of the broad nuclear fusion community has been focused on magnetic confinement. Can you explain just how laser-based inertial confinement works? So it says 192 laser beams were aligned on a deuterium tritium DT target smaller than a P.
Yes.
This is like
BB actually. Yeah.
Okay, well, it depends. Not all peas are made the same, but this is like throwing a perfect strike in baseball from a pitch. This is like a journalist wrote this, I think. This is like, oh no, it's not a journalist. It's DOE wrote.
Yeah, it could
Department
be,
of Energy.
We try to use all these analogies.
This is like throwing a perfect strike in baseball from a pitcher's mound 350 miles away from the plate. There you go. Department of Energy. The United States Department of Energy wrote this. Okay. Can you explain what the lasers
what actually happens? Yeah. Actually, there's usually mass confusion about this. So what's going on in this form of energy? So the fuel is delivered in a discrete, the fusion fuel, the deuterium and tritium, is in a discrete spherical. It's more like a BB. Let's call it a BB. So it's a small one, and all the fuel that you're going to try to burn is basically there. Okay, and it's about that size. So so how are you going to get? And it's at literally it's like at 20 degrees above absolute zero, because the deuterium and tritium are kept in a liquid and solid state.
Oh,
so
wow! So the fuel is injected not as a gas, but as a solid.
It's actually, and it's very, and in these particular experiments, they can introduce one of these, these targets once per day, approximately, something like that, because it's a kind of amazing technology, actually, that I know some of the people that worked on this back in the day they actually make these things at a BB size of this frozen fuel. It's actually at cryogenic temperatures, and they're almost like smooth to the atom level. I mean, they're amazing pieces of technology. So what you do in the end is what you have is a spherical assembly of this fuel, like a ball. And what is the purpose of the lasers? The purpose of the lasers is to provide optical energy to the very outside of this. And what happens is that energy is absorbed, because it's in the solid phase of matter, so it's absorbed really in the surface. And then what happens is that when it's absorbed in something called the ablator, what does that mean? It means it goes instantly from the solid phase to the gas phase. So it becomes like a rocket engine. But you hit it like very uniformly. So there's like rocket engines coming off the surface. Think of like an asteroid almost, where there's like rockets coming off all this thing. So what does that do? Well, what does a rocket do? It actually pushes, by Newton's laws, right? It pushes the other thing on the other side of it, equal and opposite reaction. It pushes it in. So what it does is that the lasers actually don't heat. This is what was confusing. People think the lasers, we're going to get it to 100 million degrees. In fact, you want the exact opposite of this. What you want to do is get essentially a rocket going out like this. And then what happens is that the sphere, and this is happening in a billionth of a second or less, actually, this rapidly, that force so rapidly compresses the fuel that what happens is that you're squeezing down on it and it's like, what was the... See, BB that's bad, actually. BB, I should have started with a basketball. Goes from like a basketball down to something like this, in a billionth of a second. And when that happens, I mean, you scale that in your mind. So when that happens, and in this comes from almost from classical physics, so there's some quantum in it as well too. But basically, if you can do this like very uniformly and so-called adiabatically, like you're not actually heating the fuel, what happens is that you get adiabatic compression, such that the very center of this thing all of a sudden just spikes up in temperature, because it's actually done so fast. So why is it called inertial fusion? It's because you're doing this on such fast timescales that the inertia of the hot fuel basically is still finite, so it can't like push itself apart before the fusion happens.
Oh wow!
Yeah.
So how do you make it so? How do you make it so fast?
This is why you use lasers, because you're applying this energy in very, very short periods of time, like under a fraction of a billionth of a second. And so basically and then the force which is coming from this comes from the energy of the lasers, which is basically the rocket action, which does the compression.
So is the force, is the inward facing force,
It's
is that increasing the temperature
no,
exponentially?
you want to keep the fuel cold and just literally just ideally compress it. And then in something which is at the very center of that compressed sphere, because you've compressed it so rapidly, the laws of physics basically require for it to increase in temperature.
So
The
change in
effect is
pressure.
like if you know the thing. So adiabatic cooling we're actually fairly familiar with. If you take a spray can, right, and you push the button, when it rapidly expands, it cools. This is the nature of a lot of cooling technology we use, actually. Well, the opposite is true, that if you would take all of those particles and jam them together very fast back in, they want to heat up. And that's what happens. And then what happens is you basically have this very cold, compressed set of fusion fuel. And at the center of this, it goes to this 100 million degrees Celsius. And so if it gets to that 100 million degrees Celsius, the fusion fuel starts to burn. And when that fusion fuel starts to burn, it wants to heat up the other cold fuel around it. And it just basically propagates out so fast that what you would do, ideally, you would actually burn, in a fusion sense, most of the fuel that's in the pellet. So this was very exciting, because what they had done was, it's clear that they propagated this, they got this, what they call a hot spot, and in fact that this heating had propagated out into the fuel, and that's the science behind inertial fusion.
So the idea behind a reactor that's based on this kind of inertial confinement is that you would have a new BB every
10 times a second or something like
and
this.
that there's some kind of so there's a incredible device that you kind of implied that kind of has to create one of those BBs.
So you have to make the BBs very fast. There's reports on this, but about what does it mean? The starting point is, can you make this gain? So this was a scientific achievement primarily,
right.
because
and the rest is just engineering.
No. The rest is incredibly complicated engineering. Well, in fact, there's still physics hurdles to overcome. So where does this come from? And it's actually because if you want to make an energy source out of this, this had a gain of around 1.5. That, namely, the fusion energy was 1.5 times the laser input energy. Okay, this is a fairly significant threshold. However, from the science of what I just told you, is that there's two fundamental efficiencies which come into it, which really come from physics, really. One of them is hydrodynamic efficiency. What I mean by this is that it's a rocket. So this just has a fundamental efficiency built into it, which comes out to orders of 10%. So this means is that your ability to do work on the system is just limited by that, okay? And then the other one is the efficiency of laser systems themselves, which if their wall plug efficiency is 10%, you've done spectacularly well. In fact, the wall plug efficiency of the ones used in that experiment are more like 1%, right? So when you go through all of this, the approximate, place that you're ordering this is for a fusion power plant would be a gain of 100, not 1.5. So you still, and hopefully we see experiments that keep climbing up towards higher and higher gain. But then the whole fusion power plant is a totally different thing. So it's not one BB and one laser pulse per day. It's 5 or 10 times per second. Like that, right? So you're doing it there. And then comes the other aspect. So it's making the targets, delivering them, being able to repeatedly get them to burn. And then we haven't even talked about how do you then get the fusion energy out, which is mainly because these things are basically micro implosions which are occurring. So this energy is coming out to some medium on the outside that you've got to figure out how to extract the energy out of this thing.
How do you convert that energy to electricity?
So in the end, you have to basically convert it into heat in some way. So most of what fusion makes mostly is very energetic particles from the fusion reaction. So you have to slow those down in some way and then make heat out of it. So basically the conversion of the kinetic energy of the particles into heating some engineered material that's on the outside of this.
And that's, from a physics perspective, is a somewhat solved problem, but from an engineering is It's
Yeah,
still wide open.
physics. I can show you all the equations that
Right.
tell you about how it slows down and converts kinetic energy into heat, and then what that heat means. You can write out like an ideal thermal cycle, like a Carnot cycle. So the physics of that, yeah, great. The integrated engineering of this is a whole other thing.
I'll ask you to maybe talk about the difference between inertial and magnetic, but first we'll talk about magnetic. But let me just linger on this breakthrough. It's nice to have exciting things,
Yeah.
but in a deep human sense, there's no competition in science and engineering. We're all, like you said, we're broad. First of all, we are humanity altogether. And you talk about this, it's a bunch of countries collaborating. It's really exciting. There's a nuclear fusion community broadly,
Yeah.
but then there's also MIT. There's colors and logos, and it's exciting. And you have friends and colleagues here that work extremely hard and done some incredible stuff.
Oh, yeah.
Is there some sort of how do you feel seeing somebody else get a breakthrough in using a different technology? Is that exciting? Does the competitive fire get
All of the above? I mean,
the ignition?
I have just to wave the wave the flag a little bit. So MIT was a central player in this accomplishment. Interesting, I would say it showed some of our two best traits. So one of them was that how do you know that this happened? This measurement, right? So one of the ways to do this is, if I told you, is that in the DT fusion, what it actually, the product that comes out is helium.
Mm-hmm.
We call it alpha, but it's helium, and a free neutron, right? So the neutron contains 80% of the energy released by the fusion reaction, and it also, because it lacks a charge, it basically tends to just escape and go flying out. So this is what we would use eventually for. That's mostly what fusion energy would be. But so what my colleagues, my scientific colleagues at the Plasma Science and Fusion Center built were extraordinary measurement tools of being able to see the exact details of not only the number of neutrons that were coming out, but actually what energy that they're at. And by looking at that configuration, it reveals enormous. I'm not gonna scoop them because they need to publish the paper, but it reveals enormous amounts of scientific information about what's happening in that process that I just described. So exciting. I mean, and I have colleagues there that have worked like for 30 years on this for that moment. Of course you're excited for them. I mean, and there's one of those, there is nothing. It's hard to describe to people who it's like almost addicting to be a scientist when you get to be at the forefront of research of anything. Like when you see an actual discovery of some kind and you're looking at it, particularly when you're the person who did it, right? And you go, no human being has ever seen this or understood this. It's pretty thrilling, right? So even in proxy, it's incredibly thrilling to see this. It's not, I don't know, it's rivalry or jealousy. It's like, I can tell you already, fusion is really hard. So anything that keeps pushing the needle forward is a good thing. But we also have to be realistic about what it means, to making a fusion energy system.
Yeah.
That's
and then, but that's the fun. I mean, these are still the early steps. Maybe you can say the early leaps. So let's talk about the magnetic confinement. How does magnetic confinement work? What's the tokamak? How does it all work?
So go back to that. So why inertial confinement works on the same principle that a star works. So what is the confinement mechanism in the star? Is gravity, because it's its own inertia of the something the size of the sun basically pushes literally a force by gravity against the center. So the center is very, very hot, 20 million degrees, and literally outside the sun, it's essentially zero because it's vacuum of space. How the hell does that do that? It does that and it's out of thermal. Like, why doesn't it just leak all of its heat? It doesn't leak its heat because it all is held together by the fact that it can't escape because of its own gravity. So this is why the fusion happens in the center of the star. Like, we think of the surface of the sun as being hot. That's the coldest part of the star. So of our own sun, this is about 5,500 degrees. A beautiful symmetry, by the way. It's like, so how do we know all this? Because we can't, of course, see directly into the interior of the sun. By knowing the volume and the temperature of the surface of the sun, you know exactly how much power it's putting out. And by this, you know that this is coming from fusion reactions occurring at exactly the same rate in the middle of the sun.
Is it possible, as a small tangent, to build an inertial confinement system like the sun, is it possible to create a sun?
It is, of course, possible to make a sun, otherwise you wouldn't have stars. But it is not possible on Earth because, for the simple reason that it takes the
The
gravitational
gravity,
force
yeah.
is extremely weak, and so it takes something like the size of a star to make fusion occur in the center.
Well, I didn't mean on Earth.
yeah.
I mean, if you had to build like a second sun,
Yeah.
how'd you do it?
You can't. There's not enough hydrogen around. Yeah.
So the limiting factor is just the hydrogen.
Yeah. I mean, the forces that and energy that it takes to assemble that is just mind-boggling.
All right.
So we wouldn't do that.
To be
right?
continued.
Yeah, to be continued.